It's time to introduce a new machine learning algorithm, Random Forest. It's a machine learning ensemble. Let's discuss what that means. Okay, first of all, why random forest? Okay, decision trees have issues. They're prone to overfitting, which means in effect they do not perform well on test data. Okay, this is by default. Additionally, decision tree paths may not be optimal. So the idea here is that the machine learning algorithm is going to find a path through the decision tree to arrive at its prediction. But there are limitations to algorithms because you cannot try every single split. A standard algorithm would be the greedy algorithm, and like it has limitations. It is a truth in computer science that you cannot find an optimal path when you have, you know, too many possibilities. When you have sort of infinite real numbers on every column with any possibility for a split, there simply is no way to guarantee that you can find the best path. Now, this is different than linear regression, which does find the best hyperplane. It minimizes the distance. So, what are some solutions? Well, we can fine tune the trees by adjusting parameters. We looked at that. We can lower max depth, for instance, okay? And that will, kind of help with overfitting. But there's another idea, which is to combine the decision trees into an ensemble. Okay, an ensemble is a collection of machine learning algorithms. And a random forest is a very special ensemble that we're going to talk about. But before we do that, let's just, get some clarity on how the decision tree works, because random forests are made up of decision trees. Well, here's a decision tree slide with a max depth of 2 that shows how do you get from the data set to a prediction. Well, you follow splits in the data that the algorithm finds, right? This is a pathway to get down to a particular prediction. Every row of data will go down a different pathway to arrive at a particular prediction, okay? That is how a decision tree works, and we can change the depth of these trees. Okay, recall that too large of a max depth doesn't generalize well to new data, but if it's too small, sometimes it's not picking up on the nuances of the data. Okay, here's a decision tree with no max depth. If you counted, this was from the HART data set, so I actually ran this. I think it's like 10 splits. You can count it down like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 at the max. And so in this case, any new row would follow one of these paths to arrive at a different prediction. Okay, so random forest. First of all, they combine many decision trees. 100 is the default. You can actually change that parameter, but the default is 100 decision trees. Now, these trees are bootstrapped, and that means they're sampled with replacement. This is a very important concept, so let's take a look at a graph that tries to explain this. So here is your original data, and underneath you have different decision trees. And so how does each decision tree arrive at its sample of data? Well, you can see from this one that, okay, it picks a blue one, but then it puts it back. Okay, that's what sample with replacement means. How do we know it puts it back here? Well, because this has 1, 2, 3, 4, 5, 6, 7 blue rows. Okay, these are rows of data, but the original only has 5. So this allows for diversity among the trees. Okay, it's done randomly. And you want diversity among the trees, because if each tree was the same, you would get the same prediction as one decision tree, and it would be no better. So what you do is you bootstrap sampling with replacement to get the rows of data. Then you build your single decision tree and get a prediction. But you're going to get, in effect, 100 different predictions. So you aggregate the predictions. If it's a classifier, you just take the majority. If it's a regressor, you take the mean. And bootstrapping along with aggregating is called bagging. Okay? That's what this is. This is a visualization of bagging. Random forests are a bagging algorithm. And note the keyword ensemble classifier, meaning, hey, even though these are individual classifiers, we are going to combine them into one ensemble. Okay, so randomness is involved in the random forest by choosing the rows, which uses bootstrapping, and the number of features of the columns to consider when making the tree splits. So it doesn't always consider every column, it considers random ones, and this leads to additional randomization. Okay, again, to get the diversity of the tree. So it's done via rows and columns. Okay, and now since the decision trees vary, they will in fact give different predictions. Okay, and you can sort of see why this is a good thing, because if your decision tree is, it could have a bias on a certain column, right? Or maybe it found some convoluted pathway, but a second decision tree is going to find a totally different pathway. The variation leads to sort of a more robust model. And then the random forest takes the average of all in regression to make a final prediction, okay? Or just majority rules for classification. And it is a bagging algorithm, as mentioned, bootstrapping plus aggregation. Let's take a look at the visual one more time. Here's your original data. You randomly select the rows. Okay, we get a unique selection of rows. Then when we build the decision tree, it's actually only going to look at certain columns to pick the splits, which allows for diversity also across the classifiers. We get 100 classifiers in this case, and we're going to aggregate them, combine them into one. Okay, so what are some random forest pros and cons? Pro, random forests generally perform better than decision trees. Okay, the more the merrier in some sense here. It's rare that a single decision tree will outperform an ensemble of trees. Pro, this is also a generality that goes beyond just random forests. Ensemble models often outperform individual models. There are ways to construct your own ensemble models. These will often win Kaggle competitions, I can tell you. Another pro, bagging has proven itself as an effective machine learning option. Random forest, it's a bagging option. And same is true more generally with random forest. This is a staple machine learning algorithm that is widely used and tested. Another pro is that there are ample parameters to fine tune, because you can tune not just the individual trees, but some additional parameters within the ensemble. And so it's kind of like when you have more parameters that you can tune, that allows for greater opportunity to get better results from your model. Okay, so what are some cons? The random forests are limited if the individual trees are weak. Like, if you can't make a strong decision tree out of your data, you're not going to get a strong random forest. Okay? Another con. Random forest trees do not improve with new iterations. Okay, this is maybe some foreshadowing. This is what gradient boosting does. It's kind of like, it's not really improving, right, each round. It's just sort of like, here's the trees, let's sum them up. And so it's a different kind of an ensemble that can improve with each round, which we'll discuss in a future lesson. And another con, and this could be with a lot of ensemble models, random forest can be computationally expensive. What does that mean? Well, you're building maybe 100 decision trees or more. So, let's say it takes, like 10 seconds to make one of the decision trees because you have a lot of data. Well, if you have 100 of those, that's going to take you 1,000 seconds. That's what it means by being computationally expensive. It can actually take time. So all in all, random forest, it's a really great model, and you definitely want to try it out on your data.